Welcome to the HyperLynx Theater here at DesignCon. In this presentation, we'll talk about how HyperLynx helps you verify designs quickly and cost-effectively before manufacturing by using progressive verification. Let's start by answering the question, why do we think you should fully verify your designs before fabrication? Designs continue to increase in complexity, not just by the number of nets they have, but also with component density increasing as well. These complex designs have strict requirements for how they should be routed. They include major design areas like signal integrity, power integrity, EMC, and manufacturing. Sometimes these rules are impossible to follow and you may end up bending or even breaking them. And then mistakes just happen. Some of these mistakes could have been inevitable or may have even been random and make you feel like that guy right there. The question you want to ask yourself is, will you find them before it's too late? And lastly, fully verifying a PCB is a difficult job. There's no way around it, which means you need experts, and especially experts in multiple domain areas. And a key resource of those experts is time. If you're not doing manual inspection of your designs, it's not only difficult, but also very time-consuming. And so we all know the adage, time is money. And that's especially true when trying to fully verify your PCB layout for fabrication. You may have heard comments like this when your PCB layout is complete. We routed it to the rules. Why do we need to spend time verifying it? We'll just fix any problems we find in the lab with the next spin. Or simulations take too long, we can't afford a hit to the schedule. Ironically, none of these arguments hold when a real problem is found in the lab. The time it takes to debug, rework, and redesign your board far exceed the time to properly validate it in the first place. Let's look at how some of you may be verifying your designs today. The first option is that you design the board to the vendor guidelines, then do visual inspection to look for possible errors. You then fab out the board and hope for the best. It's not a bad option for those with decades of experience. The second option is you hire an external consultant to verify it for you. But that means any changes you make to the design require another round of simulation, which means sending it back to the consultant for more money. And our last option would be that you have in-house SI experts who verify the design for you. But do you have enough of them, and do they have time to fully verify your design? Not surprisingly, we don't think any of these are particularly great options. Let's look at how HyperLynx can ensure your designs are ready for fab out. So we like to call this methodology progressive verification with HyperLynx. This methodology is built around the constraints of time and expertise. That means it has the specific goal of finding problems as quickly and as easily as possible. With progressive verification, we analyze the designs in successive stages, increasing analytical detail as we go. The bulk of the issues are found and resolved before the SI experts are brought in, so that limited SI expertise is used as cost-effectively as possible. With progressive verification methodology, we start by running electrical design rule checks during layout to look at potential problems. These types of checks don't require a lot of SI expertise, so infrequent users of the tool or those with less experience will be able to easily validate your routing rules and guidelines. And then we do standards compliance analysis. We want to look at the system level interconnects and make sure it meets the protocol requirements. Some expertise is needed here, but these simulations provide quick and accurate results for you to review. And finally, once we've gotten as many problems off the table as possible, IBIS AMI, our vendor-based model simulation to predict how the system will perform with actual devices and settings. This is where the SI expert can verify the design while being utilized as effectively as possible. The design used during this demonstration is the SDK180 board. It's based on the AMD Versal Premium Series VPK180 evaluation board. And so this design supports optical transceivers that run at 56G and 112G. It also has LPDDR4 memory on it, as well as peripherals for USB and Ethernet. The changes we made to this design include reworking the stack-up using the Z Planner Enterprise tool, and we also included some manufacturing data like backdrilling. We also put the board in a mid-layout state. So that means most of the components have been placed, critical high-speed nets have been routed, along with necessary power planes. This introduces artificial errors into the board so that we can go through the process of using HyperLynx to verify the design. This decision flow is used in each step of progressive verification to determine what steps we should take next. For each rule checked or simulation run, we ask ourselves, how bad is it? If it's bad to the point of being broken, then we'll need to fix the layout before continuing. If the problem isn't an issue, we can mark it as verified and move on. And lastly, if we're not sure if this might be a problem, we can investigate further through iterative modeling and simulation. So this brings us to our first step in progressive verification, electrical rule checking. This is done automatically with HyperLynx DRC, and we like to call this the first line of defense for progressive verification. HyperLynx DRC performs quick checks on your design to make sure it's routed according to your rules and guidelines. This means errors will be detected before performing time-consuming simulations. HyperLynx DRC can perform these checks within seconds to minutes, where other simulations can take hours or days. You can also perform this automated checking in process, which means you don't need a fully laid out board, but can run these checks as the board is routed. HyperLynx DRC flags and marks issues automatically. It also documents them so that we can find the issues later on in the design. With our SDK 180 board, we wanted to verify the 72 56G nets on the board. Protocol Compliance analyzes system interconnects for compliance with the applicable standard. In this case, we are using the CEI 56G VSR PAM4 protocol. This step is useful because most designers design interconnects with standard off-the-shelf ICs and connectors. You may ask yourself, why not run the analysis that focuses on what you actually design? Compliance analysis works because serial link standards establish requirements for channel electrical behavior that can be analyzed and verified. Better yet, compliance analysis doesn't require IBIS AMI models, so it works even when vendor models aren't available, and it offers good accuracy for verification purposes. HyperLynx currently includes built-in support for 256 serial link protocols and variants. They all run from a common interface, so when you know how to run one of the protocols, you know how to run them all. Best of all, HyperLynx knows to configure and check all the metrics associated with each standard, so you don't have to remember all the nitty-gritty details. Compliance analysis produces a full, comprehensive report that shows which links passed, which links failed, and by how much. It also produces eye diagrams along with time domain, frequency domain, and TDR plots of channel behavior. It is a great first step in quantifying how your channel performs at the system level. And so this brings us to the final step of progressive verification, which is device-specific or IBIS AMI simulation. As shown earlier in the presentation, IBIS AMI simulation builds upon the critical 3D areas and channel models created from compliance analysis. The results from compliance analysis helped us figure out which nets are the worst performing that we need to focus on. IBIS AMI simulations add the I/O models, packages, and device programming for the specific ICs you're using in your design. This provides the highest level of accuracy and is generally used for sign-off and where the design's operating margins are really small. IBIS AMI simulation also takes the longest time and requires the greatest amount of expertise on the part of the user. As a user, you need to know if you're going to run time domain or statistical simulation and all the settings that go along with each of them. Finally, device-specific equalization controls need to be understood and set up properly. IBIS AMI models are usually obtained individually and under NDA. And as we said, IBIS AMI simulation is the most time-consuming and expertise-intensive step in the progressive verification methodology. Performing complete system-level verification with traditional techniques is a daunting task. Design rule checking, compliance analysis, and IBIS AMI simulation involve multiple detailed steps that can affect analysis results. If we're going to analyze a design repeatedly as layout progresses, then performing these steps consistently is critical to success. Any complex process performed manually is subject to error, so automating the entire process from front to back is essential to producing usable results. Automation allows us to scale the process. Let's look at an overview of the steps required to fully verify this design. We start by importing the design data, and then we'll get our models and make sure they're assigned to the correct components. We'll then do some parameter setup around vias, pad stacks, and any coupling we want to do. We'll then select the nets that we want to analyze. We'll automatically extract those 3D areas for analysis. We'll run the analysis and then analyze the results. HyperLynx uses automated intelligence to ensure the process is consistent and accurate. We use Python as a common automation language between all tools. That means each step in the process can be combined into a single flow that can be launched with a single click. This level of automated intelligence is one of the key factors in leveraging our advantages over other EDA tools. Post-route verification is a race against time. The moment the layout is complete, the pressure is on to send the board out for fab. And you're never exactly sure when you'll run out of time for verification. Progressive verification lets you find as many problems as possible, as fast as possible, so whenever that time is up, you've done all you can to make sure your design is as error-free as possible. We talk a lot about scaling simulation capacity and performance, but it's also important to scale simulation based on the user's skill level. SI and PI experts are in perpetually short supply, and the problem isn't getting any better. Because progressive verification uses staged analysis steps, the first parts of the process are accessible by non-expert users, which helps offload dedicated SI/PI staff. This means the SI/PI experts can be used more effectively and in more technically demanding areas of your process.